All right, everybody, welcome back. Our last speaker of the day has a degree in astronomy and is the chief photo and video analyst for the History Channel television series, The Proof is Out There. He is also the MUFON's chief photo and video analyst. He is the host of Sky Tour Radio and KGRA and creator and CEO of the popular Sky Tour Livestream. Sky Tour Livestream, or STLS, is a group of live deep space telescopes, observatories around the U.S. that broadcast live on YouTube and other social media. He also is a consummate performer and no stranger to the stage. He has an extensive work history in television, discussing and investigating extraterrestrial life, appearing regularly on networks such as History, Discovery, Discovery Plus, Netflix, TLC, CNN, and more. And he has also appeared on several seasons of NASA's Unexplained Files, What on Earth, and Unexplained with William Shatner. He is also the CEO of FX Models, a model-making and visual special effects company specializing in digital and physical models and organic visual effects in the film industry. Please join me in welcoming Marc D'Antonio.
I'll tell you, this guy,
And an all-around nice guy.
Forrest, thank you so much. You know this guy, right? Oh, you can't hide from everybody. They know you. I've been told by the folks back there that I can't leave the stage. They blocked me in. If you're familiar with me, you know that I love to go out in the audience, right? And it's like, okay, I won't. But I have stairs here. Okay, first of all, how many of you have seen me talk before? I'm just doing a poll. Okay, all right. How many people saw the Y-Files episode I was just in? Okay, not too many. Okay, good. So you're in for a treat, because I'm going to be talking about some things there. Here. I want to do a little experiment first before we go. And I told my friends over there that this is what I was going to do. How many of you thought of someone you haven't talked to in years, and the phone rings and it's them? Raise your hands. Look around. Okay. Science tells you that's a coincidence. What's that tell you about science? It tells you that, now I'm an astronomer, this is what we look like, minus the tie. Okay? But the fact is, science doesn't have all the answers, does it? We can't explain that. And when we don't know something, I say we, collective, doesn't include me. When we don't understand something, we say it's a coincidence. It's not. They say it's a coincidence, a series of coincidences that led to us. Life on Earth with as much intelligence as we think we have. All right, watch it there. It's true. But the fact is, we are on a planet, okay? Our planet is just a beautiful big blue marble, right? And we definitely have abundant life here, all right? And this abundant life that we have, all right, is through a bunch of different creatures that have developed one characteristic that is common among all of them: curiosity. Every creature is curious. That beautiful cattle dog back there, Parker, okay, by his mom, is curious. What's that? What's that? You know? Okay, curiosity is something that every creature has, including us. What do we do with it? We try to find other life like us. Why not? We're carbon-based. Life in the universe is probably carbon-based. All right, now, remember that ugly periodic table? Everybody hated that. I can sing it. I can. There's hydrogen and helium and lithium, beryllium, boron, atoms everywhere, carbon. Okay, I'm not going to bore you with that. However, I did that because I wanted to understand the periodic table and all those groups that it has. And if you look at carbon in the periodic table, right below it is silicon, Si. Okay? Silicon and those elements that are just under carbon are all the elements most like carbon. So the next most likely element that could foster abundant life would be silicon, besides carbon. But the problem is that carbon is very flexible. Carbon is amazing. It can bond with and break bonds with more things than any other element in the periodic table. And that means one thing. If you go down to silicon, silicon has a problem too. Silicon bonds with things, but it doesn't let go. It doesn't let go. So that means that if you have silicon and you bond it with two oxygens, very common. Oxygen is the third most abundant element in the entire universe. Did you know that? Know what the fourth is? Carbon. Second is helium, first is hydrogen. Okay? So carbon stands to reason that it has a love affair with oxygen, and it does. All right? Now, the point being, when silicon bonds with oxygen, it makes silicon dioxide. What is it? Someone knows. Sand. What's beach made of? Sand. So when you tell your friends, when next time you walk on the beach, you're walking on mostly gas. I'm walking on sand. Yep, mostly gas. 2 out of 3 of the atoms are oxygen. Go back on a towel and just be quiet, right? That's what you'll get, right? So, but again, our curiosity led us to discover all these things. Our curiosity leads us to think, what else could foster life on our planet? Okay, well, we do know that there's a lot of biomes, different ecological niches on this planet that have life in it. We didn't even know for a long time that there was abundant life in the deep ocean. Who knew? I know why. We weren't there, right? Alvin, Project Famous, 1975, went down to the bottom of the ocean, the Juan de Fuca Ridge off Oregon coast, and they found smoking chimneys. They called them black smokers, sulfide vents, okay? And these sulfide vents were spewing mineral-laden water that certain bacteria loved. And so there were bacteria around these plumes of mineral-laden 900-degree Fahrenheit water coming out. The pressure keeps it water and not boiling. So what happened? Well, creatures that love to eat bacteria flourished. And creatures that ate the creatures that ate bacteria flourished. And you had these little tiny, oases of life on the ocean floor. I have a tiny piece of a smoker chimney that the folks at Woods Hole gave me. It's really cool, you know. So, and pardon me for clearing my throat once in a while because I'm not sick or anything, but I'm missing a vocal cord. Yeah, I'm doing this all with one vocal cord. Go figure. Who knew we needed 2? Yeah, so it works. So as a species, took us down to the bottom of the ocean. Because we went down there, we noticed these hydrogen sulfide chimneys. And because we went there and saw that, we noticed that there was life down there, which made us think, wait a minute, let's look outside Earth. Let's look at other worlds that might be in the dark. Not Venus. Mars was a candidate. We always thought, Mars might be a candidate for life. But how about moons of the large planets? How about Europa around Jupiter? How about Enceladus around Saturn? These are ice-covered worlds. And the Cassini mission at Saturn, so far away from the life-giving sun, found evidence of hydrothermal vents, like in the bottom of our ocean. Does that mean mineral-laden water with bacteria could be down there? We don't know. We're going to find out. Europa, geysers, plumes that have all kinds of minerals in there that are building blocks of life. Is there life under that ice mantle? There's oceans under there, just like at Enceladus. Why would we have water so far away and such cold? Because as the moons go around the planet, Well, the planet's pulling on them with its gravity, but there's other moons going around them too, and it literally kneads them like dough. That process geologically heats up the core of the planet. So this is what happens to Europa. This is what happens to Enceladus. Okay? And so the heat inside of Europa can support an ocean that's about 90 miles deep. Now, we have 7 miles deep on Earth, okay? But 90 miles deep on Europa, that's pretty deep. But because it's so small, only about 2,000 miles across, you can go really far down and not feel as much pressure, you know? Because the gravity's not that powerful. So, all that said, our curiosity drove us to the outer solar system looking for life under the ice, and we're still doing it now. We're going to find that we have the Europa Clipper that just got launched. It's going to circle Europa, and then it's going to look for a suitable landing site for the Europa lander. And it's going to land in one of these big crevasses, because there's big crevasses, and it's going to see if it can drill down into the ice and get to the ocean. That's kind of scary. Who saw the movie The Europa Report? Oh, look that up. It's a fun movie. It's about a trip to Europa, and they find something. I'm not going to tell you. They give it away, you know. So the bottom line is then that, okay, we have a curious species. There's no doubt, okay? And our curious species, also found a black hole around a distant galaxy, inside the distant galaxy. It's called a supermassive black hole. Now, this was found in a galaxy called the Virgo galaxy, okay? And the galaxy was amazing because it was 55 million light years away from us. It was actually a very big black hole that we found. And we used 8 observatories around the world. As the Earth spins, you have 8 different locations. Each time it spins, it takes a swath of radio data from this location and basically makes an 8,000-mile diameter crude telescope. The bigger your diameter telescope, the smaller the object you can see. And that's what this did. This is an image of a black hole. Now, you say, well, is the black hole the round thing in the middle? Sort of, kind of. Okay, that's an area where light isn't getting to your eye because something's keeping it from getting there. Okay? Aha, you're that guy. That's fun. Whenever the cell phones go off, I do that just for fun. It means nothing. We all do it. We all do it. I'm not casting judgment. So this was the New Horizons telescope that actually made this detection, and it's really cool. And we did it again with our own galaxy. But if you look, okay, it's the equivalent of making a telescope that could see the date on a quarter in Los Angeles from Washington, D.C. That's the kind of resolution it was. So that's the image. Now, that's human ingenuity. Look at us go, you know? Really cool. Now, that black hole thing in the middle, that's actually what they call the event horizon. It's actually the shadow of the event horizon. There's some physics to go into, I'm not going to do it, to describe why this isn't exactly the black hole, but you know, it has to do with the event horizon. Makes every black hole look like a donut from whichever way you view it from. Anywhere else in the universe, it looks like this. That's how it looks. Okay? Now, interesting thing is, that stuff along the bottom looks brighter than the stuff along the top, doesn't it? There's a reason for that. Okay, if you think about black holes, if you know anything about them, you know that there's a supermassive black hole in the middle, and then it has what's called an accretion disk, a disk of material whirling around it, kind of like the sun has planets. Well, this is a disk of accretion material going around, but it's got a lot of gravity. So the light leaving that disk on the far side of this black hole, trying to go up, gets bent around because of the gravity. So you're seeing the top here of the other side. This is like looking down on top of the other side, and this is the near side. So it's literally a perspective illusion based on the amount of sheer gravity that you're actually looking at. Isn't that weird? Yeah, astronomy's weird. I'm weird. Yeah, I've known that for a long time now. So the bottom line is that, this tech to find this is a little bit different from finding planets that may have life on them. But it shows that our capabilities have really come quite a long way, right? Now, this image shows the unforgiving nature and destructive power that's out there in the universe. If you're anywhere near this, you would not get sucked into it before you were eviscerated by the amounts of radiation that's being emitted from it. Okay, and that's just not a kind thing to talk about. Okay, now this galaxy in the constellation Virgo, the Virgo galaxy, is not the only place where this is happening. It's happening here too. Here's an image of it. This is a GIF. You can see the animation. Notice where the plus sign is. We're going to zoom in. All right. Now watch as the stars go by. Whoop. Okay. Watch this big one. Ready? Whoop. You know what that is? Those are stars over a 10-year period whipping around the supermassive black hole in our galaxy. Look at that go. You see the curved paths and whoop. Yeah. So that star could have planets around it. That star could have life. But as it gets closer to the black hole, there might be a disruption to that stellar system, and those planets go bye-bye. It's pretty interesting how that happens. Now, we're going to take another journey now. We're going to come back to Earth for a minute. There are processes that allowed life to form on the Earth, all right? But Earth was also predisposed to generating life of its own as well. So many of the building blocks of life have been brought here by things like comets, okay? Comets, that's a comet, okay? This part here, this is called the dust tail. It's basically going to trace out the orbit of the comet wherever it goes. Okay, this is the ion tail. These are ions, that is, atoms that have had their electrons stripped off, and they're just streaming back directly away from the sun. Okay, it's always pointing directly away from the sun. It's blue because the ions are blue. They glow blue. This is just dust on the comet. So every time a comet comes by the Earth, it loses a great proportion of its mass. And it ends up being smaller and smaller and smaller and smaller and smaller until there's nothing left, right? And that's the kind of thing that comets do. One such comet that we managed to actually land on was this one, Churyumov-Gerasimenko. This comet, I didn't just sneeze, that's actually the name of the comet, okay? The Rosetta mission sent to look at this comet circled the comet as it was coming toward the sun. That's a really strange-looking object. It doesn't look like an asteroid, doesn't look like a planet. It has its own look. And the thing that's interesting about it is all these craggy areas here. Now, the Rosetta satellite actually released a lander called Philae, not F-I-L-E-T, but P-H-I-L-A-E. Again, we love to confuse you. And the Philae lander landed on it, but it didn't have enough gravity to get held down by the gravity of the comet. So we had these hooks that were going to hit and fire into the ground and hold it there, anchors. The best laid plans often fail big time, as did this. The Philae ones went down, they tried to fire in, bounced off the comet, came down 15 kilometers off the comet, and then came back down, did it again and again and again and again, 10 more times. And so it ended up lodged in the crevasse, and that's the only way it stopped, okay? So there's very little, you could jump off this comet and be free, so you'd need to be tethered if you're on this comet. So again, they're small, a few miles across, but they have their own gravity, it's just small, right? But looking closely at it, you can actually see some really interesting features. I mean, it looks kind of like the moon in a way, right? But there's very smooth areas here, very craggy areas here. Now, what does it mean to see a smooth area here? That means something that resurfaced itself. Because this stuff over here, okay, is older material, right? Because that's been there for a while. But this is sort of new. There might be rough stuff underneath it, but this stuff kind of oozed out and went on the surface and then got coated with liberal amounts of space dust, But we saw a lot of interesting compounds on the surface of this comet that were all carbon-based, And it's actually known as Comet 67P because Churyumov-Gerasimenko is too hard for many people to say. Wow. It's like, don't run with the scissors. I say that because I mean skizzers, right? So yeah, it was covered in this fine dust, but there was many different organic compounds. And comets have struck us and brought building blocks of life to us. So the universe provides, almost as a template, the building blocks of life, doesn't it? Now, as an aside, there's 3i Atlas inside the red box. We took that with our SkyTour live stream test, our system actually, out in Benson, Arizona, when it was out by where Jupiter is. Right? Now, this is a time exposure. So we went for several minutes deep in the constellation of Sagittarius, and we actually caught this tiny little dash right there. That little dash right there. You see that? That's the comet. Okay? Notice I'm calling it a comet. I'll get to why. Okay? It's really a little tiny dot, but it was moving a very, very small amount of time every minute, or a distance every minute. So if we left many minutes open and let the sensor build up an image, we'd get a tiny little dashed line. That was my hope. So I left it open, not knowing what we'd get. I was right on the coordinates, and that's what we got. So we caught it when it was 5.2 astronomical units away, out where Jupiter is in its orbit, but not where Jupiter was at the time. So that was it. Now, the thing is, there's anomalies galore. You heard Avi Loeb at Harvard talk about them. I've worked with Avi a few times. He's a great guy. I applaud him for stepping out to say we should at least consider the extraterrestrial nature of objects we see. I applaud him for that. I think that's a great thing. No one in academia, especially a Harvard chair of astrophysics, should be doing that, right? But it shows there's a shift now in academia. This is excellent. Now, whether right or wrong doesn't matter to me. What matters is he's willing to say, could it be? That's all. Could it be? He never said it was. He said it could be. And he was crucified for that. By who? By his own academia, right? Okay, the academics. Right? They're not ready for it. But you know what? He was. And he's changing the tone, and I applaud him for that. A really good guy. Now, this is the problem, okay? It had this excess nickel. Remember hearing about this? 3i Atlas, okay? And the excess nickel is a problem, because when we see nickel in the periodic table, usually you see iron as well, okay? Iron and nickel, in fact, they're so common being seen together, we have a nickel-iron ratio, Ni to Fe. Fe is iron, Ni is nickel. So Ni over Fe, put the two numbers in, and you get a ratio, a value. And we expect to see a ratio that it's actually, what we expect to see for comets that we know, right? We didn't see that with this, okay? We saw something very different. We saw a lot of nickel and no iron. No iron. Wait a minute, what's that? Well, keep in mind, this was an extraterrestrial object, okay? It came from another star system. It's also possibly 7 to 8 billion years old. Or as Carl Sagan would say, 7 to 8 billion years old. My favorite astronomer, I love that guy. 8 billion years old, meaning the solar system wasn't even around when this thing started its journey. Right? So all this time moving through deep space. So what could it have encountered? It could have encountered carbon dioxide molecules wherever it went. It could have encountered other kinds of elements and compounds. It could end up with more of a certain kind of compound than another. What's that important for? Well, because when we look at something like this, we try to determine its composition. If we know its composition, okay, then we can determine what's inside of it and how it might have originated. And that's what we did with this. Okay, now the excess nickel could be explained by a couple things. In a comet here, in our solar system, we see carbon monoxide, CO. Okay, carbon and an oxygen atom. We can't breathe it, of course. Bad for you. Okay, but carbon monoxide, the silent killer, okay, is something very prevalent in comets. Now, nickel can do something. Nickel can bond with carbon monoxide, and you get 4 carbon monoxide groups around a nickel atom, and you have something called nickel carbonyl. Yay, Carbonyl, nickel carbonyl, okay? And now, we didn't see anything except nickel. Now, in order to free the nickel from those carbon monoxide elements, or molecules, you have to have a temperature of about 100 Fahrenheit. As it approached Earth and approached the sun, that temperature reached there, and we started to see nickel. But wait, what about the iron that's supposed to be there? Well, there was missing iron, and the missing iron was possibly, and I say possibly because none of this is shown to be true yet, but I believe it is. Mark my words. You'll remember, you heard it here first. Okay. Iron can also bond with carbon monoxide and make iron pentacarbonyl. So 5 carbon monoxide groups on an iron atom. Okay, what does that mean? At 200 degrees, iron pentacarbonyl vaporizes, releasing the iron atom. So as it got even closer, more iron started showing up, and we started to see the nickel to iron ratio we expected. Oh, darn. You mean it's not an extraterrestrial spacecraft hull? Look, I was on board with all these anomalies. There were a bunch of different anomalies. I was on board with that. I said, hey, that's cool. I like anomalies. I want to find them too. That's why I started taking pictures. But the thing is, when we looked at this, typical, sorry about the size. I'll read it. The typical comet has 12%. There's an excess of carbon dioxide too. That's the other thing I wanted to mention. Way more than we expected. Typically, we'll see about 12% carbon dioxide to water. Okay, the ratio. But on this comet, there was 140% carbon dioxide to water. Way more. Again, keep in mind where it came from. It came from another star system. Now, everything we know about comets, we put together through our science, and we say, we know what we're doing. Comets are comets. We know what comets are in our own solar system. We don't know what comets look like from other solar systems other than Comet Borisov, which came through just before this one. And Borisov looked okay. This one is the oddball. This one was also perhaps 33 billion tons in mass. That's huge compared to our comets. So it's a special comet, that's for sure, okay? We don't know exactly how special, but it's definitely a special comet, without a doubt, okay? So that's this excess and all these anomalies made for one heck of a mystery. Now, the path through the solar system was also one. How would an ordinary comet coming in from another place decide it's going to pass by Mars, circle around the sun, pass Venus, and on the way out, pass by Jupiter? Hit 3 of the major planets in our solar system. Now, the thought is, if we were building a probe to do it, we might go to another star system and hit as many planets as we could, too, and pass them, right? That's what we would do. So this looked kind of intelligent, I grant you. Science would call this a coincidence. Okay? And maybe, just maybe, in this case it is. There are real coincidences, okay? So the bottom line is, okay, when it got closer, this is what we saw. Okay, I created an image. This is over an hour and a half in the skies of Benson, Arizona with our telescope. You're looking at Comet 3I Atlas. Okay, you see the core is this greenish color. You see a tail that's extending back slightly. Okay, and it shows a dust tail like all normal comets. Yeah, it shows a green tinge like all normal comets. Okay, this green tinge comes from something called cyanogen, and when the sun's light hits that molecule, which is 2 carbons and 2 nitrogens bonded together, you end up seeing a green glow, because as it splits that apart into 2 CN molecules, they can be ionized and make a green glow. So we're seeing a green glow. You also see carbon atoms bonded to each other, which make a green glow as well. So the green glow is characteristic of comets. So as it turned out, 3I Atlas turned out to be not such an enigmatic object after all. I was crushed. I was hoping, I wanted to see, there were some things. Lights seen on 3I Atlas. No, that's AI. Okay, here's the latest picture of AI Atlas. No, that's the planet killer from Star Trek that you put in there and elongated to make it look like that. Who saw that one? Okay, it was terrible, So, the hoaxers came along and just went crazy. But anyway, so 3I Atlas, I figured I'd just put that in for today so you could see what's going on here. Now, Earth, again, as I said, was predisposed to hosting life. We're in the habitable zone. Now, what's a habitable zone around a planet? It's the place around a star where the temperatures aren't really hot, so much so that they would boil water. This would allow liquid water on the surface. That is a habitable zone. We're in a habitable zone. Yay. Trouble is, our planet is not what we call super habitable. Uh-oh. Super habitable is a planet where you don't have tectonic activity, but you still have nice climate. It's a planet where you don't have an axial tilt, so you don't get killing winters. It's a planet where you don't have any type of earthquakes or anything like that. It's a planet where you don't have a lot of volcanic activity that can hurt you and kill you and destroy all your people. We have all that, and still we're here. Look at us go. We're troopers. However, it has limited us, and it has possibly stunted our evolutionary advance. 252 million years ago, the creatures that would become all of us, pre-mammals, way back then, they were rising to dominance when all of a sudden there was a major volcanic eruption in what is now Siberia. And that spewed billions, there we go again, billions and billions of tons of carbon dioxide into the air. It raised the temperature on the planet 21 degrees Celsius in a few weeks. The ocean, think about it, that's massive increase in greenhouse gas, coated the whole planet. And that means that what happened then is that all the life that depended on oxygen in the ocean was being starved because oxygen doesn't like hot water. It doesn't like to stay suspended, so you don't get as much oxygenation in salt water as you need. And so a lot of those creatures would die. And this is a problem. We lost 96% of all life on the planet at that point. Almost set to zero, guys. So then what followed was several more extinction events. But I'll tell you this, when that occurred, the Permian extinction, the pre-mammals, the things that would become us eventually, were locked in the shadows. We were minimized, minimal, retreated into the burrows, retreated into the distance. And so what was left was a warm planet, a planet that other types of creatures could thrive in. Who knows what those were? Yes. What? Cookie. You get a cookie. Very good. Yes, it left the way, it paved the way for dinosaurs, and thus began the age of the dinosaurs. Okay. Now, the age of the dinosaurs lasted for almost 200 million years. I mean, they did very well, right? And then, of course, pow! Knocked out by the Chicxulub impact, the day the Earth died again. And when that happened, there was 76% of all life on the Earth died. Who knew? Okay. And that included dinosaurs. What happened was the asteroid struck off the Yucatan Peninsula. The major dust cloud went up into the high atmosphere, went around the globe, or on the upper air currents, extinguished the light for a lot of the plant-eating, for the plants. The plants died. The plant-eating dinosaurs said, hey, no more food. They died. And then the meat eaters, the theropods they were called, that ate the plant eaters, ran out of their food supply. And so ding, 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 they cascaded and died. Had that not happened, something I talked about with those guys right there a little while ago, we would have seen potentially the rise to dominance of a species based on dinosaurs, maybe. We all hear the term reptilian, right? I used to laugh at that term. I used to say, how stupid could people be? All right? You know where this is going. I was the stupid one. Okay, I admit it. I'm not proud. I have no ego. So when it comes down to it, when you talk about the potential for dinosaurs being smart, they had every opportunity. And they would have had every opportunity had they not been rendered extinct by a single impact off Yucatan. How would that look? Well, let's say it never happened. At the time, there was a dinosaur called the Troodon. Okay, and that dinosaur was actually increasing its cranial capacity, its ability to think and reason by a tremendous amount. And so this was going to become potentially a dominant dinosaur amongst the others. Okay, it learned how to utilize caves for protection. It learned how to utilize sunlight. It learned how to shelter its eggs and not just leave them out in the middle of the ground and say, where'd my eggs go? You know. It was pretty smart. It started to reason things. It got up to like probably about as smart as as Parker, the dog back there, okay? It was probably about as smart as a dog, okay, when it was rendered extinct. So had it not gone extinct, maybe you'd all have tails and yellow eyes, talk differently, look a lot uglier. I don't know. I don't know what a reptilian would look like. Maybe better, who knows? I don't know. So the point being that this type of thing then, it wiped us out. And so this asteroid striking did that, okay? Now, other meteors have struck the Earth with life-giving qualities and elements, such as the Murchison meteorite. The Murchison meteorite had a number of amino acids in it. Hey, amino acids are building blocks of life. That's right. Okay. Now, we also find that the Earth itself could create the building blocks of life. Who's heard of the Miller-Urey experiment? Yeah, I didn't think so. You know why? It's boring. But not for us. Okay. The Miller-Urey experiment was very interesting because they put it in a flask. They put what they thought might be the primordial atmosphere of the Earth, and they bombarded it with a spark. They ran it for a week. They evaporated water to make like atmosphere and water vapor, and they put in CH4, methane, NH3, ammonia, diatomic hydrogen, 2 atoms of hydrogen, and carbon monoxide, that CO we talk about. And they bombarded it with a spark for a week. And at the end of the week, when they looked inside here, guess what? They found amino acids, the building blocks of life, created by the Earth itself. What's the spark up there in this? Well, lightning. Okay? What's the atmosphere? Well, whatever was in our atmosphere, this is what we expect was in the atmosphere at the time. So we actually found out that the building blocks of life were delivered, and so life could possibly grow and be fostered by this process. So we have comets bringing in stuff all the time. We have meteors hitting our planet with amino acids. And we have the Earth itself making these things. So this means Earth itself could actually be forming the life. And I think, here's how it works. I think that Earth and the universe provide templates for life, okay? Carbon is the 4th most abundant element, as I mentioned, in the whole universe. 4th. That's a lot. There's a lot of carbon, more carbon than any other life-bearing element, element at all. So it means to me that if you can have a carbon life form, it's probably going to be the basis of life all over the universe. I'm a carbon bigot, okay? I'm sorry. I'm not a silicon guy. All right? But I am a carbon bigot, and I do believe that carbon is probably the way to go. So guess what? If you're carbon-based, you need another element in order to survive all the time. We just talked about it. It is oxygen, thank you. You guys are so smart. I'm going to go. They don't need me. Oxygen is really important. So if we have oxygen out there, and we see oxygen in a planet's atmosphere, well, then perhaps we're looking at potentially life. On our planet, and this is unfortunate for all of us, on our planet, we have a copious amount of oxygen that is created by phytoplankton, right? All right. Well, they don't create it because they say, let's make oxygen. No, that's what they're pooping. You're alive because you're breathing bacteria, waste, poop. Never smelled better. Okay? So obviously that bacterial waste product is something that is going to happen on other worlds potentially. So if we see a planet, as we may have with other oxygen signatures in it, if it's a real big quantity, it's probably going to be life, guys. It's not going to be geologic. Oxygen doesn't like to stay in an atmosphere. Look what happened to Mars. We haven't looked at what happened to Mars. You look at Mars. Mars had a really thick atmosphere, kind of like our own at one point. It had oceans just like our own. Did you know that? You probably have heard that. Where's all the water? Well, see, Mars also had billions of years without a magnetic field. The magnetic field saves us from the Martian fate. The reason is because when Mars' geomagnetic field started to drop, okay, it meant that ultraviolet energy and high energy particles could reach the surface. And when that happened, as the atmosphere thinned, UV wasn't stopped. When that happened, then water molecules evaporating from all that copious water on the surface, well, they go up there. H2O goes up into the air, and the ultraviolet radiation hits it, breaks it apart. Now you have two atoms of hydrogen. Off it goes to space. The oxygen says, "Wait for me," and it can't. It's too heavy. It goes down into the ground, where it bonds with iron. Okay, very common on Mars. So that happened for billions of years, and over time, all the water kind of was photodisassociated, it's called. Big words, right? And all the water was literally disassembled in the atmosphere. All the water vapor turned into the hydrogen and the oxygen. So what happened? The oxygen dives into the ground, bonds with iron, and you get rust. Mars rusted, and that's why it's red. Thank you, I can go home. No. But the point being, that whole process took billions of years, but it happened because of a lack of magnetic field. And that is something that's really, really, really important. Now, after you look at this, you see that the Earth made these. We got amino acids. We saw that asteroids, meteors, comets delivered these things to us. Well, now, when we had the first life on Earth, it was these phytoplankton, these cyanobacteria. Okay? Now, plankton are a form of cyanobacteria, okay? And so these guys, all right, were like the little green slime you see on rocks, the stuff you slip on and fall in the lake by accident and curse the little green slime. That little green slime is why you're here. A little more respect, please. Kidding. Okay. Another version of this is these guys, stromatolites. I think this is Australia's northern coast. Stromatolites are interesting. A lot of algae forms on the surface of rocks, even in the ocean. And that surface layer, the algae live for a certain period of time, then they die. And then sand sticks to the bodies of the dead algae, and then more algae grows on top. Okay, so you have algae, sand, algae, sand, algae, sand, algae, sand. And the thing is, they're light lovers. They're phyto creatures, so they love the sun. So when they grow like this. And they become like little mushrooms like that. All right? So these mushroom formations are like the oldest living fossil on the planet, which is kind of cool, right? Who knew about stromatolites? I expect to see a few hands. Yeah, see, you guys are smart. There's some geologists in the audience. I love it. Okay, so now let's talk about the solar system and life elsewhere, because that's something that I think is really, really, really important. Okay? Now, we know that life requires water. We're very familiar with that, okay? We also know that our solar system has plenty of water in it, okay? Witness Europa, Enceladus, water vapor spewing from all kinds of places elsewhere. We even know the moon has water on it. Now, there was a mission called L-Cross, which dropped a rocket body into a crater called Cabeus, C-A-B-E-U-S, on the moon. And they looked at the splash created, because it was a crater on the south pole of the sun. I was going to say the sun. South pole of the moon. And that crater was always in the dark. So because it was always in the dark, like I'm going to get now, they're looking at me, no, don't you do it. When you get into the dark, water could survive in there potentially. And they thought, well, maybe there could be water in there. So they crashed this rocket body and looked at the splash. Sure enough, water vapor being splashed up from the moon. So there's water on the moon. Okay, we're going to build a colony in the south pole of the moon. Is that a good idea? I mean, I don't really think so. Certainly not in a perpetually dark crater. How are you going to get energy? Can't put up a solar panel. This thing ain't working, There's like no sun, So there are some definite handicaps with doing that, for sure. All right, so I guess we have to say it's not going to be easy to put a colony on the moon, except when we looked at elsewhere in the moon, we found out that in the lunar regolith, that's the word for soil that we try to confuse you with, the lunar regolith actually has a lot of water bound up in it anyway, kind of all over the moon. So we might be able to extract water that way. Now, see, I had an idea. This is coming from the guy, don't forget, that as a 9-year-old made a space station plan and sent it to NASA. I did. Yep. And you know who read it? I'll tell you who read it. A scientist down there read it, and he wrote me back as a 9-year-old and said, this is great stuff. Stick with, they called it the manned space program. Stick with the manned space program. You're going to go far. You know, I don't want to go out there. I want to stay here. Okay? You know, you go out there. But he said, you're going to go far. Stick with it. And he gave me all these comments, and he sent me a big box full of models, patches, books, brochures, all with his own money. Okay? That guy, I always give him credit because thanks to him in part, a great part, I'm an astronomer today. Because he took a little kid who was only interested in stars and planets, you know, to try and overcome a fear of the sky because of a missing time episode, okay? He took that little kid and turned him into an astronomer. His name is Gentry Lee in Pasadena at JPL. Okay, he's in charge of the Outer Space Robotics Directorate. He may have retired by now, but I called him 45 years after the fact, and I said, you may not remember me. He didn't. But I was that 9-year-old kid I sent the space station plan to, blah, blah, blah. And he laughs. He goes, oh, my gosh, that is the kind of thing I did. And several other people that know him told me that is the kind of thing he would do, you know. And he said, I don't remember you in particular, but that's so cool. What are you doing now? Oh, I'm an astronomer now. Oh, fantastic, right? I said, and I owe it to you, man. Yeah. For me to get where I am, wherever that is, I've stood on the shoulders of giants. So I can't claim the credit for me. It's them, right? So I always bring them with me wherever I go because they deserve that, you know? So and I know that's an aside, okay? But, you know, from the kid who sent that space station plan down to NASA, I began to wonder about life in our solar system as a little bratty 9-year-old. I'd pester my mom frequently about, I want a telescope. Like, it was making her crazy. So what do? They bought me a telescope. I don't recommend that, you know, to parents to tell their kids that story. So I ended up looking at the moon, astonished by the moon. Oh, my gosh. And then I started looking at the stars. Now, I had a missing time event, and as a result of it, I ended up in the hospital because I had seizures from it and convulsions that very night. And I don't know what happened. I still don't to this day. And people say, you should be regressed. No way, man. I'm scared. I'm not proud to say it. I'm not too proud to say it. Anyway, so I asked for a telescope because I wanted to learn a little bit more about what it was I was afraid of up there. Because I felt I was being watched. All right. So a little thing in my head telling me that, okay, and you guys can relate. Some of you feel this way now. Okay. But you're being watched by me. So as I was looking in the sky and saying, I got to figure out what's going on up there, I trained my telescope on the moon. Okay, that was fine. Then I looked at a star, and it was like frightening. I mean, the star was dancing around because of the light and everything. I didn't really know that as a 9-year-old, but it was really cool. And then I gradually came to feel that if there's something out there, I'm going to find it. Okay, and I really got militant about it. So I decided I'm going to have to try and find out what's going on up there. I want to know what's happening. So I ended up deciding to go further in astronomy, and then Gentry Lee solidified it. You know, telling me that's effectively saying, that's the right way to go, man. You know, so that's what I did. Now I'm up here talking to you about stuff, having stood on the shoulders of giants. And we continue now by looking at water in the solar system because this is how we're going to discover life elsewhere, is we're going to look for things that are happening here that could be happening there. All right, one such place is here. The Cassini mission to Saturn. Okay, this is Enceladus. It's a moon of Saturn. It's only about 300 miles across. Yet it shows us these really strange spikes coming off it. What are those? Those are geysers of water spewing out of canyons at the South Pole. Well, what are those things? I mean, these are pretty incredible, all right? Those geysers happen to be something that tell us a little bit about this moon. It's tiny, but it's being squished, as I said, and kneaded like dough by Saturn and Dione and Tethys, the other moons around it. All right, their gravity is tugging on it and squishing it little by little. All right, so this water now is focused at the South Pole. That's the South Pole. And when Cassini passed over it did a map, a thermal map. And guess what? It showed a tremendous amount of heat in all those geyser points, just like we see at the hydrothermal vents here on Earth. So had we not found hydrothermal vents on Earth with Project Famous in 1975, Woods Hole Oceanographics Alvin, same little guy that found Titanic, had we not found that, we wouldn't have given it a second thought about being an oasis of life possibly under there. But because we found that, we said, hey, hydrothermal vents, could they be related? And that has led to an entire science of exobiological study trying to find potential life underneath the icy mantles of these distant moons. I think that's pretty cool. It's pretty cool. So it's not only in Enceladus that we see this water evidence, as I mentioned before, Europa. Okay, Europa is an incredible moon of Jupiter. You have Jupiter, and then you have Io, the closest moon. Okay, sulfur-laden, has a cloud of sodium atoms around it. You have Io, you have Europa next, then you have Ganymede and Callisto, the 4 Galilean satellites. Those little buggers are the ones that got Galileo arrested. Because he said, these things go around Jupiter. What? Heresy. Lock them up. There was no room for science back then, right? So Europa is phenomenal. It's literally about 1,920 miles across. It's really not that big, okay? And it's one of these moons that has this icy sheath, and then underneath it, looks like it has this vast ocean. It could be 90 to 100 miles deep. Now, it's potentially very briny, that's salty, okay? But it goes down pretty deep. Now, could it be that life could have happened in the dark down there and formed in the dark? I believe it could have. Okay, now when we look on the surface, it has these craggy valleys like this of ice. Now, it may be vast. This may be a little exaggerated. It might be like it's more sloping and everything, but these are big valleys and cracks. These cracks indicate that the surface crust has broken apart and come back together. Broken apart, come back together. Sort of like tectonic activity, but not the same as ours. Just ice-based, okay? And on the surface, we see the places where this stuff is breaking out. Okay, like right here, we're looking at areas on Europa where material has oozed up to the surface. It's brown, okay? It's carbon-based organic compounds coming out of the center, or coming out of the ice, okay? What's that mean? Well, it means that Europa could be a factory of life's building blocks underneath its surface. So that's why we want to get through that ice. How many miles thick is it? The ice is thicker than our crust, okay? So it's pretty thick ice. And we're going to have some kind of a drill to get through it. Probably a nuclear drill. Yeah, hope not. But possible. There's a heat-based concept in the docket right now. You go into the deepest canyon you can find. Like this guy right here is deeper, for instance, than this one. Okay, so that's a deep shadow. That's probably a U-shaped canyon. Okay, so you go to a spot we can pick, and that's what the Europa Clipper is going to do. When it gets there, it's going to circle Europa. We're going to get unprecedented views of this little moon. That little moon is going to be laid bare to us, and it's going to be amazing. So you go to one of these really deep spots, okay, and you land. And then the concept is we drop a singular rod that is superheated and let it drill through the ice. by heat. And then once it gets through the ice, we pull it back up, and we send down a little camera or a little mini sub. That'd be pretty cool. We can make a submarine this size that delivers all kinds of... I've done it. I've made them. High tech. This big. Okay? And for me, it's easy to do. So imagine if someone had hundreds of millions of dollars. They could say, your concept stinks. Look at ours. And then they have this amazing technology, right? That could be. So again, Europa is a phenomenal opportunity for us to maybe find life. So here's what it looks like inside. It has a rocky core, okay? All right? And it has this deep ocean, 90 to 100 miles, okay? And when looked at with the Hubble telescope, it looks like this. This was 2012, right? These guys right here, you see these things here. This is carbon, hydrogen, oxygen, all spewing out of Europa, all this. Okay, so you see it all around Europa. This stuff is just omnipresent there, okay? Now, a follow-up mission with James Webb, okay, shows 2021 we had water all through Europa's orbit, and it makes a tail around Europa of sorts. So there's water following it around, okay, because it's being released from Europa, okay? Then, of course, as Europa orbits Jupiter, what's it do? It runs back into that water, and it goes back onto the surface again, all right? So it's pretty cool. Fun fact about the closest moon, Io, to Jupiter. That little guy, and when it gets behind Jupiter, it's now behind Jupiter, it's in the cold. So the sodium atoms in the atmosphere of Io, very tenuous atmosphere, rain out like snow and fall to the surface. And then Io, on the other side of Jupiter in the shadow, has no atmosphere at all. So then when it comes back out, those sodium atoms get vaporized and go back into the atmosphere. So it has an atmosphere that comes and goes. Okay, glad it doesn't happen here. Okay, yeah. So the James Webb Space Telescope found also carbon dioxide trailing the moon as well, and it was determined it came from inside the moon. So that's really cool. Now, there's a composite of Europa, so you can see where the geyser's location is. This is the stuff that is so important, that we just pass over. We're here to talk about aliens and UFOs and things like that, and Bigfoot at times, right? But when we talk about all those things, we want to put them into a framework that we can understand, a framework that says, here's how they can be here, here's why they might be here. We have a very, very lucrative solar system for them. They have all the water they need, if they want, okay? They have life to study, tag us, send us on our way, right? Yeah, and they do. I'm convinced. Those of you who know me know I had an implant, I think. Okay, 3 nights of terror. Something got shoved up there. Surgeon took it out at Hartford Hospital. This is all public record, by the way. At Hartford Hospital, Hartford, Connecticut, where I live in Connecticut. Okay, and a week after he took it out, I called to ask whether they found anything, because I told him about this weird experience I had where something shoved this up. It was a gray hand that shoved this thing up there. And I didn't know what it was. It was sort of a glowing wand kind of a thing. All right. Now, I'm a science guy. What do you do with that? What do you deny it? It happened. So I told him the experience, and his response was, I'm sure it's not aliens. And I went, aliens. So he said, call me in a week, I'll let you know. I went, okay. Called him in a week. Yeah, he said, yeah, it's Marc D'Antonio. Hold on, doctor has to talk to you. Uh-oh. I felt, uh-oh. It's like my head going to fall off, like, because what have I got going on there? Hey, Mr. D'Antonio, I just want to let you know that it's probably benign, nothing to worry about. Oh, so you didn't get the results back from pathology? And I heard crickets. I said, Dr. Lehman? And he goes, well, here's what happened. Here it comes. I've been doing this for 40 years. This is the very first time, he said, this has ever happened. What's that? I sent this sample down to pathology, and they seem to have lost it. Welcome to, I don't know, what is it? I said, okay, well, thank you, doctor. And I hung up thinking, okay. So I went to him again 2 years later. This is an aside, yes, it's not exactly this, but we're getting back, don't worry. And I went back to him again 2 years later for something else. And this time, when I went in, I filled out, the intake form you do. Well, I always put all kinds of cartoons on it because the medical assistant, my wife's a medical assistant, and she's bored to death by these intake forms. She has to correlate them, read them. So I draw cartoons and funny faces, and I do all kinds of silly things. I say I'm female when I'm male. I say that I'm lactating. I'm sorry, but I do. Okay. I say all these funny things just to get a rise out of the medical assistants. And he comes in with that form. He goes, my medical assistants love you. And it's, well, I'm making their day, ain't I? Because they're getting all the boring stuff. But down in the occupation part, I said, I'm self-employed and I do special projects for the Navy. I did. For decades, I was very high up there doing projects. I've worked for the president. Okay, I've worked for the Joint Chiefs. And so I spent a lot of time doing that kind of work. And I told him that. And he did something I never saw a doctor do in the entire time I've gone to doctors. I guarantee it's never happened to any of you. He jumped up on the exam table with me. That's awkward. And he sits there, hand at his side, crosses his legs like we're two kids on a pond, like overlooking a pond on a cliff. He's swinging his legs, and he wistfully says, I just gave up my top secret clearance this year. What? And I tried to hide that. I said, really? And he said, yeah. And I said, you? What you? I said, did you work on top secret nasal polyps? And he goes, no. He goes, and he got really serious. I wasn't always a surgeon. And he proceeded to tell me about a project he worked on in the Pacific with the Navy when he was in the Navy. And you know this project, some of you. Starfish Prime. We launched a nuclear weapon to the ionosphere and exploded it for the purpose of figuring out what a nuclear weapon can do to the ionosphere. Look at it go. Lit up Honolulu from 1,500 miles away for a split second. When he did that, he told me that. I said, well, what does that have to do with anything? He goes, we weren't testing the ionosphere. We took out an enemy satellite with it. EMP. Oh. So this was an EMP test to destroy an enemy satellite. Exactly. Wow, you don't see that in Wikipedia. Right? I think I actually said that to him. You don't see that in Wikipedia. And he goes, what? Old school. And so he didn't know what I was talking about. But so he said that he worked on this project and that they retained him as a consultant for years. And so he would do the consulting project work. He would end up doing that, but he kept his clearance, TS, all the way. Well, TS, top secret. And he finally just gave it up. Now I know what happened to that thing they took out of my nose. Yeah, you heard. Okay. The problem is, and when you're in that world, and I was in that world, I gave up the clearance some years ago because it's too invasive. Okay. I had someone, I don't know who, put bugs in the walls of my shop. I don't know who did. Probably one of the electricians people or something that came through. They found the bugs. Now you're on a list. Oh, no, they've got bugs. You found bugs. Whatever. So I'm going to get out of the program. So I did. I still get the work. It's just not the classified work, which is fine. So I said to the doctor, so you worked on top secret stuff, huh? He told me about Starfish Prime. And then I thought to myself, okay, here's how the call goes then. If it happened to me, I'd be obligated by law, federal law, to call and report a potential violation that would be something that the National Security Agency, the NSA, would want to know about. I don't want to report anything, but you're obligated by law. You can always say, I didn't see a thing, and you'd be fine. So I never called anybody on anything, except one time, which I'll tell you. But that was about a UFO result. So the call went something like this. He called down there and he probably said, yeah, I got a patient here. This will be my phone. I got a patient, okay. He said he had a terrifying encounter with a creature or something that shoved something up his nose. Yes, that's right. Hartford Hospital, right? It's in pathology. Okay, where is it now? It's in room blah, 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 whatever the lab was in pathology. Okay, thank you, doctor. Okay, bye. And that's it. He gets off the phone. He has plausible deniability. Under polygraph, under oath, he can say, I don't know who has it. He's right. I don't know when it was taken. He's right. And I don't know anything about it. I don't know where it is now. And he's right. So that's what happens when you have a clearance. You are only given a narrow slot of things you get to know. You don't know what's over here. You don't know what's over here. Another time that happened was when I saw that USO on a U.S. submarine. Okay, I was a guest on the boat for doing some work for the Navy. They had me go out, and something whizzed through the sonar at hundreds of miles an hour. Okay, and when I went up to the XO, I asked them, they called it a fast mover. I said, I can help. I know what these fast movers are, sir. Can I help you? He goes, D'Antonio, right? Sir, yes, sir. Having a good trip so far? Sir, yes, sir. Let's keep it that way. I wasn't in the Navy, but I had a clearance higher than most of the people on that boat. Didn't matter. If you're not read in, you don't get to know. Nah. Okay, fine. And that's fine. But then I had to do a job for the Joint Chiefs 2 years later. I went down, delivered it. It was a model for the Office of the President, and I went and sat with one of the chiefs, and I said, now they call this thing a fast mover, sir. What can you tell me about the fast mover program? Anything? He looked me right in the eye and said, sorry, Mark, I can't talk about that program. It's real. It's real. I almost peed my pants. I'm not kidding. It was like, that's astonishing. Our Navy has known about them for a long time. So part of our science of finding life elsewhere is related to why we're looking so hard. We're looking so hard to find out, are they stationed at Europa? Are they stationed on the moon? Are they on the far side of the moon? Lunar Reconnaissance Orbiter has been orbiting the moon for years, mapping the near side, the far side. Have you seen Lunar Reconnaissance Orbiter quick map? Who has? Raise your hands. Okay, you've seen the quick map. That's it? Okay, I'm about to end marriages. I'm about to end. Okay, can't make the game. I got to look at this. Okay, the Lunar LRO quick map. All one LRO Lunar Reconnaissance Orbiter. Don't worry about that. Just say LRO space quick map QUICKMAP. You will get a map of the moon you have never seen before. Clearly, it shows every crater on the moon in extreme detail, down to things the size of half of this room. Okay? You can see the lunar modules on the surface. You can see the tracks left by the astronauts. You can see the experiments on the moon taken from the lunar orbit, okay, by the LRO. Okay? That stuff is all freely available. I took it a step further, wouldn't I? Okay? I wanted to find, see, when they came off the moon, they left in this ascent module, the upper part of the lunar module, and they docked with the command module. Then they released this thing and let it go down and crash on the moon. I found those crash spots. You can see an explosion of debris on the moon in LRO quick map. So take that, moon landing deniers. Okay? Oh yeah, I can prove you wrong 6 ways to Sunday. And I will. So we look for life elsewhere. We want to find life. We look on the moon. People say, oh, there's life hiding on the moon. LRO has dispensed with that. But then you say, well, NASA just scrubs the images. Come on, okay? Did the Japanese do that too? Have the Israelis done that too? Have the Indians done that too? Have China done that? Well, China might, But, all these nations that are on the moon now, okay, none of them have done that. None of them have scrubbed their data like this. You'd have to have a worldwide conspiracy. We can't let the whole world know what we all know, that there's something hiding on the moon. Now you hear old Apollo astronauts, as they get older, they say, oh, what we saw on the moon was crazy. It was like they told us to leave or whatever. I take that with a grain of salt. I've had dinner with Apollo astronauts, okay? Alan Bean, okay? Alan Bean and I had dinner at the old Avon Farms Inn in Avon, Connecticut, okay? I sat with him, and we talked about the moon, and he basically became an artist because of it. He said it was the most spectacular-looking landscape he's ever seen. Stark, yet beautiful in its own right. He found color where there was none. And the moon is all colors. It's not just gray and dark gray. It's orange, it's got white, it's got shades of blue, okay, in the soil. And we just don't see that with our cameras, the way they take the pictures right now. But it's there. Anyway, so we're trying to find the building blocks of life on the moon. We found them. You know, even the moon, a dead world, no real atmosphere. It has a tenuous atmosphere. I don't think anyone knows that. But it's not of anything we can breathe, all right? It's actually just some atoms of sodium that are floating around the moon to make kind of a sort of tenuous atmosphere, and nothing to even worry about. But the thing is, that's so amazing. Now, we look further out, we go to Europa to see if there's life there. Well, we don't know, okay? But so we have to look even further, don't we? So we got to look out into the universe even farther. What about looking at other worlds in the universe, okay? That's another place to go. So we'll leave the moon behind, leave Europa behind, leave Enceladus behind, leave the Earth behind, not for long. And then we come back. And what do we see? Well, we see that we're going to find ways to locate planets that planets that might be orbiting their stars. Now, this was just a dream when I was getting my astronomy degree, okay? I talked to my director, and I told him, his name was Art. I said, Art, I think it's a populated universe. And that turned out that was a very important line for me because I made that the title of my book, The Populated Universe, right? That's not a sales pitch. I'm just telling you the truth. Okay, so I said it's a populated universe. He says, why? I said, well, because look, we're carbon-based. We're bilaterally symmetric, the same on the left as the right. Every single life form on this planet shows symmetry of some kind. Symmetry. There isn't a life form that shows no symmetry. It has symmetry. That's based on what? I said to him, I said DNA. When DNA unzips, it makes a complementary strand that zips up to it. Symmetry. And that symmetry is extended to the macroorganism. And that's why we're symmetric. That's why cows are symmetric. That's why we don't have one-legged cows, boing, 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 okay? Because of symmetry. I told him, I did do the boing, boing thing. That probably is why he thought I was an idiot. But, and I told him, I said, so I think it's a populated universe. I think there's life out there, and I think it's normal. I said, I think it's the rule, not the exception. And he was a fairly heavy guy. He had suspenders, right? And he always had his glasses down like this, as you can imagine they would do. And he goes, Mr. D'Antonio, get back in the observatory and leave Captain Kirk to us. And I was like, okay. Well, as it turns out, I was right. For all the reasons that I suggested. The symmetry of our bodies and our existence is something that is born out of a planet that has a carbon base and oxygen. And when we look at the Kepler Space Telescope, it's looking for planets that may have these elements, all right, or just may have a sign that there's a planet going around the star. And that's what this particular one did. It searched for over 530,000 stars, and it actually found over 3,300 planets on its own. Okay, on its own. We're not talking about the other stuff yet, because the number is much higher. Okay, because here's the total. Other exoplanet searches have turned up 6,153 planets total so far. And these are just targeted looks at this part of the sky, that part of the sky, that part of the sky. Okay, the front row right there. No, I'm just kidding. Okay, right? But that's the targeted view that we're taking. And so we're finding it there, but there's a lot of those little points that we haven't looked at yet. And when we talk about transits, that's the thing that is interesting here. That's how we're finding the planets, okay? So here you have a double star. That red one's a small red dwarf star. There's a yellow one behind it, and there's a planet in front of it, right? Now, this particular double star has a transiting planet. It's going in front of the star as seen from Earth. This is a hypothetical, okay? Now, that means that transiting planet is going to block some of the light from those stars. So what we're going to see coming from the main star is this. I'm going to exaggerate it. You're going to see the light from the star, planet starts to go in front, planet's going in front, planet's all the way in front, planet starts to come out, okay, off the edge, and then it's back. It's off the side of the star. You're going to see a dip in the light. We call that a light curve. You see a light curve, well, then you're going to be able to say, hey, if that repeats, we're going to then say this could be a repeating thing. So if it happens once, maybe it's a star spot, like we have sunspots. Those can do the same thing, right, to make the star look dimmer for a period of time. But if it happens over and over again, over and over again, over and over again, exactly the same way, planet. Using that technique takes a while, but doing that, we found over 6,000 planets. But that only works when the planet's going in front of the star as seen from Earth. What about planets doing this? We're not going to see those. Okay, what about if the planet's sort of on a little angle, just enough so it doesn't pass in front of the star? I know it's passing in front compared to you, but this is what it looks like, okay? All right? It doesn't pass in front of the star. Now what? We're not going to see it. So how do we detect it? There's a number of ways we can detect it, okay? We'll leave it at that. But there's one thing is the star itself, if you got a big Jupiter-sized planet going around it, then the star is not just going to sit still. The star is going to move a little, okay, in response. So we're going to look for this motion of the main star. That's called a strometry, trying to find the motion of the star. If we can find that, well, then that means that something's tugging on the star and making it move around. Kind of a little dance. Okay, I'm having too much fun. All right. So that's the thing. Now, going beyond that, okay, if we can't see a transit, well, Kepler just looked at one star at a time, like a laser. So it took a while to get to the 3,300 it found. But how about this? We have this new one here. This is TESS, the Transiting Exoplanet Survey Satellite. TESS, okay, this is a wide field. It's got a 24 degree by 96 degree field. So it's looking at many stars at once. Many, many stars at once. So with the stars that are like this, what it means is this particular object, okay, versus Kepler. Kepler looked at one star at a time. This is looking at thousands of stars at a time. And it's expected to find many, many thousands more. And I say expected. It's already done. When we got the data is massive, okay? If you could pile reams of paper starting at the corner of this room all the way to the ceiling, we'd fill this room if each page of paper was a data point for a potential planet around another star. TESS has that much data sitting out there. And right now we're working on one of those stacks out of a whole room full. So we've got decades worth of data to go through, okay? Pretty cool. Now, it's got like, right now there's 8,000 TESS objects of interest out there, and there's potentially many more to be gleaned. And there's just 8,000 that are currently being looked at of the pile of reams of paper, all right? So after that, now, this is looking for planets. This is also looking for planets. This is the James Webb Space Telescope. By the way, in case you always wondered what this big thing was, okay, that's just a sun shield. It's multi-layer, okay, to actually fully and prevent sunlight from heating up this layer, which translates to this layer. So putting this many layers means this layer remains actually at absolute zero. We want that because the back end of this telescope behind these mirrors here is the most sensitive infrared system ever made. So, and it's a 21-foot mirror. So that's a giant sun shield. This telescope needed over 300 plus individual events to happen exactly correct for it to be deployed. I watched every single one of them. I was like, please work, yes, okay, one, okay. By the time I got to 320, I was like, 320, oh, yep, okay. So after a while you get kind of tired, but I watched every one of them because I wanted this to work. I was so excited when it did. And then it took a picture of a planet. This is the first picture ever taken of a planet around another star in the infrared. Now, let's talk about the infrared and why that's something. Because if this width of this podium here, which I hate podiums. I don't like talking about podiums. You know that. If this represented the visible spectrum, the thing that all of our eyes can see, red, orange, yellow, green, blue, indigo, and violet. If this represented the visible spectrum, we see here, Hubble sees out to about here in the infrared. a little bit. James Webb doesn't start until the door. Okay, that's sort of a calculation I did. Actually, it's not false. I did this. At the door, that's when the James Webb vision starts, and it goes further. Okay, and that helps us to see things early in the universe, because the farther they are away from us, the redder they are. So things that far out are going to be so red that all of their data is no longer in the visible spectrum, no longer even in the spectrum part that Hubble can see, but way out there. And we've seen galaxies, and of course James Webb ruined our cosmology. Yes, it has, because James Webb found the galaxies out there that are fully formed at only 200,000 years or so after the universe began. Fully formed galaxies with spiral arms. It takes tens of millions of years for a galaxy to form. We thought. Well, what are you looking at here, pal? You're looking at a fully formed galaxy right there, pal. What's that mean? It means that we're wrong. I'm not afraid to say we're wrong, and most astronomers these days are not afraid to say we're wrong. We know what we know for what we know now. How about that? Well, I don't even know what I just said, but you get it. We only know what we know for the moment, okay? Now, the James Webb, okay, the star itself, no, there's no five-pointed stars out there, right? Okay, yeah. Disney did this. No, this was actually the indicator where the actual star is, and that kind of fuzzy black ring, not a black hole like we talked about earlier, that's actually the artifact of what's called a coronagraph. Telescope systems like this have the ability to block the star's glare. Okay, now if we didn't block this star's glare, that planet that we see right there, which is somewhat of the distance of maybe Neptune from the sun, okay, the glare of the star would extend far beyond the frame and maybe come all the way out to here. So you'd never even see it. You'd never have a chance of seeing that. Stars are only ever points of light. But they're so far away, we can't see their actual diameters, except for a star like Betelgeuse or Antares. Yes. Big stars. Big supernovas coming. Won't hurt us. Okay. So that said, obviously that's incredible. Now, this is a 400 light year distant planet. Okay. But the James Webb is seeing it. That's really impressive, you know. So the question becomes, all right, now if we're pushing out into the universe looking for life, where might aliens come from? What might they look like from these different types of stars? This is a good part. No commercials here. Okay? All right, so first of all, when we talk about what stars are available that can actually support planets, we have to go to this diagram. This diagram is called the Hertzsprung-Russell diagram, or HR diagram. This snaky line you see right here going down the middle here. I'm sorry on the other side, you probably can't see that, huh? I can't really do it from here, can I? But it's that snaky line right there. How'd I do? Did I make it? Almost? Okay, good. Thank you. Well, that snaky line is called the main sequence. That's the line where normal stars hang out. And these are the stars that actually are working on fusing hydrogen into helium like our sun. It's called normal fusion. Okay. You can have giant stars doing normal fusion. But when they stop that process, then they evolve off and they become giants, subgiants, and supergiant stars. Betelgeuse, Antares, okay, Rigel. Okay, these are all stars that have left the main sequence. They've left the building, man, and their ultimate destiny is supernova, especially if they're massive. Now, so when we look at this, one of the things we learned about this is that stars right around A and on down can support planets, and stars around F and on down may be able to support life like us. We're getting somewhere. So that kind of helps us. Now, the thing is, when we talk about other worlds we found, we got to talk about them in terms of the planets around the particular star that they are. We know about this one, Proxima Centauri b. This is a fanciful image. I know that it's hard to see, but there's actually two stars there. There's one and two stars right inside there. And then this is Proxima, the little red dwarf. But if you were around Proxima Centauri, this is how it would look. Okay? This is how it would look. All right? And you can see, here's where Proxima is on that diagram down here. Proxima is a normal red star. It's called a red dwarf. Now, red dwarfs are tiny. They're so small that the planets around them, if they are going to have any chance of being habitable, they have to be really close to the star. So close that they're tidally locked to the star like the moon is tidally locked to the earth. We have the same face of the moon facing us at all times, don't we? Well, those planets are always facing the same side to the star. And their days, their days are equivalent to their year, right? Because they actually have endless sunlight, okay? And they have endless night. Think about the real estate option there. I'm not kidding. Think about this. On the sunlit side, beaches all the time. Sun and beaches. Yeah. Go to the Terminator. You like sunset photos? All the time. We can't say 24/7 because we don't have that here. But using the same analogy, forever sunsets and then forever starlit nights. Right? Now, I bring that up both to be funny and to make a point. The backside of those stars is probably where life is going to develop. Now, the front side of those stars is going to be pretty hot, right? It's going to be scorching hot. So hot that life may not have the opportunity to develop there. So if that happens, they may be on the sunset part of the Terminator, just a little beyond the Terminator into the dark side. That might be the sweet spot for planets like this. And if they develop there, what might they look like? Now, what if they develop further into the dark side? Well, it's fully dark on that side. So what might life look like? What do cave animals look like on Earth? What do they look like? What color are they typically? Yeah, white or gray. Did he say gray? And those that have eyes? Like grays, gray aliens. So we hear a preponderance of evidence about these types of weird gray alien creatures that are here on Earth. What would life look like? That might be gray alien from a dark side of a red dwarf planet. Maybe Proxima itself, Proxima b, the planet there. We don't know, but I will say this. These creatures, if they exist, might be pretty high in number. Why? Because those stars, those red dwarf stars, the very first star to come in existence from our 13.8 billion year old universe isn't even 1/100th of the way through its life. Those stars are trillions of years old, and they can last trillions of years. So that means that the first one that existed is still going strong. And it's going to continue. And if you're trapped in a perpetual, tidally locked state around that star, the sunlit side is going to get bathed with flares that come from those red stars. We know they're flare stars. But the backside will be fine. So with atmospheric mixing, it might be actually pretty temperate on that side. And you might be able to evolve. We're used to evolution on our planet and how weird evolution works here. But evolution there, where it's pretty much the same all the time, might look very different. Remember what I talked about way at the beginning? If Earth didn't have an axial tilt, how would Earth look? How would life look? It'd be very different. And if our sun was closer and our planet was tidally locked to the sun and the sun was less output and we had a red star too, then life might still develop here. And we might have had a multi-million year head start on life here. So this could all be virtual. We wouldn't need cell phones anymore. These would probably be built in evolutionarily into our heads. Instant communication, who knows? Transporters, Spock, beam me up, right? That could be real at some point in that way. So obviously these little red stars then, they're long-lived. And so planets around them, long-lived. The opportunity to develop life on these planets, long-lived. So it's possible that the gray type aliens may come from there, and that means that the grays outnumber other types of aliens in the universe, and that maybe we're an oddity. And they look at us and go, "Look how ugly these things are." Yeah, right? They might. We don't know. Right now, okay, the nearest star to us is Proxima, and there's several. Okay, we have. It's a triple star system. We have A right here, and then we have B, and then we have C, okay? And A, B, and C are these, the triple stars. Now, A and B are really far away from Proxima in that way, so it doesn't really affect it. It'll just be like two bright stars in the sky of Proxima, about as bright as maybe Venus, okay? But next to each other. That's pretty cool. And then this star is kind of way out there orbiting separately, and it has at least one, maybe two planets, and it's going around Proxima, And who knows if this rendering is sort of like the Terminator side, near the sunset side? Well, okay, that's pretty cool, right? But this isn't the only place where this could happen. We have this solar system too, this star system, TRAPPIST-1. TRAPPIST-1 is interesting. TRAPPIST is the name of the planetesimal and planetary investigative system here, or research system, a set of telescopes that's looking at the sky constantly. TRAPPIST-1 is really interesting because here we're looking at a star that's way down here, even lower than Proxima Centauri. Proxima is about here. TRAPPIST is a smaller star and redder, meaning cool. This horizontal, OBAFGKM, that's in terms of temperature. Hottest and bluest is O, coolest and reddest is M. All right? The sun is a G, right there in the middle. All right? So again, not super habitable because there's a planet with a lot of activity on it, and that's ours. Hello, right? So TRAPPIST-1 is a really interesting system because these planets here, all right, I'll show you actually. We look at these planets right here, okay, E, F, and G. Okay, these three are in the full habitable zone of this star. Three planets in the habitable zone of this star. This is amazing. This is crazy. Yeah. So when you look at this, then we see the possibilities for life being kind of distributed from here. This planet may be a little warmer than this one, which is a little warmer than this one. This may be the coolest of the three. Okay. Then this one might be a little cooler still, but it's these three, E, F, and G, that may actually be the ones. Maybe F is the sweet spot, and maybe F is where there could be life form there. And if that's true, wow, this is pretty cool, So, again, these worlds are small, okay? If you look at the details, and you can't see them, obviously, but I can just tell you, okay, this right here, this planet here, the most likely one that's habitable, and the next most likely one, its year is 6 days long. It goes around the star in just 6 days. This one here, 9.2 days. The next one, 12 days. So when I said red and small to be in the habitable zone, I wasn't kidding. Mercury takes 88 days to go around the sun, and it's nowhere near habitable, is it? So if you put this star where our sun is, okay, Mercury would be an ice ball instead of a molten ball, instead of a hot ball. Yeah, so that's interesting about these small stars. And it makes more sense to talk about Jupiter and its moons than it makes to talk about our sun and its planets when you're talking about these small stars. In fact, we found one of these little red stars that's about the size of Jupiter and a little smaller, but it has a lot more mass in it, and it can become a star. If Jupiter had 80 times the mass it has, we'd have a second star in our sky. 2010, the year we made contact, remember that movie? Right? They put mass into Jupiter and made it into a star. All these worlds are yours except Europa. Attempt no landing there. Great movie, So anyway, so there's a lot of really cool stuff, a lot of cool planets. Now, Kepler's Hall of Fame has a bunch of habitable planets. This number hasn't really changed that much. I got to tell you about one discovery by James Webb. James Webb found a planet out there that's fairly large, and this particular planet showed a chemical signature that is something that only is created by life. Does that mean James Webb found life? Maybe. Now, that chemical signature is something you know. You all know this. It's called dimethyl sulfide. See? Oh, you don't know it by dimethyl sulfide. But you do know it every time you go down to the ocean and the tide's out. Oh, that's dimethyl sulfide. And it's only created by life. It's a waste product created by life. And that waste product, okay, unlike the oxygen, which is a waste product that keeps you alive, makes you go, ugh. But it was found in the atmospheric study of a very, very distant planet. And the planet had an atmosphere not of water and oxygen and nitrogen, but of hydrogen. And it's called a Hycean world, Hycean, Hycean. And this Hycean planet actually had a dimethyl sulfide signature in the water, which tells us that in the water anyway, there could have been life. But with a hydrogen atmosphere, see, we're starting to break the glass ceiling of what we know about life and what we think life is. Unbelievable. There's so much to this. It just goes way, 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 way on. Okay. Now, one of the things we also talk about is what stars I mentioned before can harbor life. So this is pretty much the same. We see a lot of M-type stars, K-type stars. These stars, now, we have to add to this one more, and that is A-type stars and F-type stars. That's 2, isn't it? Yeah, it is 2. Okay, so the stellar types are O, B, A, F, G, K, M. The colors, hot blue to cool red. And starting with the A's and down to A, F, G, K, M, we can find planets. Okay, what we found so far are these, but we found some others, which you're going to see, that are around different stars altogether. So these planets are possibly giant planets, so it's gas balls like Jupiter. Okay, and when Kepler was looking, Kepler only had the capability of finding the bigger planets. It couldn't find the small rocky ones like Earth. Now we can. So we're doing that, So we also do ground-based views. This one here from the Gemini Observatory on Mauna Kea. I talked to some of you. Some of you was at Mauna Kea. Raise your hand. Yeah, okay. You guys that were at Mauna Kea, did they talk about the Gemini telescope there? No? They did? They may have. Yeah, because it made a groundbreaking discovery. It was the first time in human history that a telescope could look at 3 planets moving around its star. Again, this is not a black hole. This is the artificial block we put, like putting your hand up to the light. I can suddenly see all of you. Now I can't. Now I can. Now I can't. Okay, well, anyway. Now I can. So obviously that's the kind of thing then that is groundbreaking. So when we talk about this particular star, we're talking about a star that's over here. It's in the A's. See that? And it's called HR 8799, a very romantic name. Okay? Honey, would you like to see HR 8799? Oh, please, the way you talk to me. Yeah, we're kind of boring too, So 8799 is really cool, all right, because we saw planets around it for the first time. And here they are, in motion. This is over the years. Okay, notice the time. Okay, 2012 to 20, was that? Yeah, thank you. Yeah, 2016. Yeah, so over those 4 years, we actually watched those planets move. Now, look at the distance up there. You see the distance at the bottom? 20 astronomical units. Neptune is 30 astronomical units. Okay? So this planet right here from the center of the star, that's this guy that's coming in right there. That one, That's like Neptune distance from its star. These guys are out in its Kuiper belt, like that outer belt of icy objects we have around our star. All right? But see, the universe is so big that we can't see close to a star very well, except when it's transiting. Obviously, there's no transit here. Remember what I talked about? Unless we could direct image a star and see its planets like this, we'd never know this had planets around it, because they don't pass in front relative to our line of sight. So that's what we get. But we have this capability. But there we go. Another example is this one, Fomalhaut. Fomalhaut is an interesting star. Okay, let's just go here for a second. Fomalhaut is, again, another A star. You see it right there. It's a little earlier than the solid A. It's just about an A star. I can't remember the A0, 1, or 2, but it's in there somewhere. And Fomalhaut actually did this. The coronagraph blocks the star here. That's the star Fomalhaut. And then we found a dust ring around this star, a ring of dust, like we have around our planet, our star. We have a ring of dust. Who's heard of zodiacal light? Okay. The zodiacal light is effectively the visual of the dust around our solar system. And you can see it really well at a couple points of the year when it's backlit by the sun. Okay? At our observatories in Arizona, you can see it with a naked eye with no problem, because it's really dark. I know I keep pushing that, don't I? And so over here, all right, there is this tiny little object. And we noticed from 2004 to 2006, it went from here to here. So we found a planet out in the dust ring of Fomalhaut that's in formation. I won't say it. Don't worry. Happens to the best of us. Okay, I can talk to him. Hi, he's busy right now. I'll get back to you. That's all right. So again, look at the distance down there. That's 100 astronomical units, and that's from the star. So this star is, this planet is literally more than 100 astronomical units away. Again, Neptune was 30. This is 3 times that distance from Neptune. That's way out into the Kuiper belt, well past Pluto. So we got all this activity that we can see. And again, in this case, look at the dust ring. It's kind of on an angle. It's going to be circular, but it's sort of on an angle to us. So it looks, this circular dust ring, when you lay it on a little bit on its side, it's going to look like this, which looks like an ellipse to us. Okay? And that's what we're seeing here. Now, again, Fomalhaut is there. Okay? Now, who remembers the whole concept of the star that was dimming over years called Tabby's star? Who remembers Tabby's star? Anybody? A few. Tabitha Bayagian was amazing. She actually discovered in the Kepler data a star that looked like it had been dimming. And then looking at old records of the star, she found that it was dimming for about 100 years of photography. So what's going on there? And one of the concepts was that maybe Tabby's star was, possibly, surrounded by dust or whatever. A swarm of comets or something caused this or whatever. Tabby's star is firmly in the F category, okay, over there, all right? It's just an F star. It's, again, could have planets and could have life. So then, but Tabby's star was neat because it was dimming for since 1890, right, by up to 20% at a time. That's pretty big, okay? So that's something that could not be explained very easily, and I bought that. I truly bought that there had to be something there. Now, it defies explanations so far, and that's still true. They don't know what's causing it. Now, the potential causes were, if you recall, there might have been a swarm of comets that went around the star that made its light look dim. But the problem being, it would have to dim it, and then it would come back, right, after they passed. Well, that didn't happen. So that was out, okay? Planets in collision. Well, that could happen, but the collision would cause a dimming that would then just stabilize. Well, that didn't happen. So then another one was maybe there was Kepler instrument error. But that didn't happen because the Kepler instrument was looking at other stars as well, and they didn't show any signs of the same problem. So this was unique to this star. So that didn't happen. So what could it be? Now, could it be that we're looking at maybe a Dyson sphere? This was the thought. This is obviously what they call a technosignature, right? When what is a Dyson sphere? Encase your star in a gigantic sphere. I tend not to believe that one, and here's why. A Dyson sphere would require technology that simply couldn't exist, because you would have gravity of a star pulling on some gigantic sphere all the way around it. And metallurgically, and even with advanced concepts that we can even imagine, it could never support that gravitational tugging. Okay, it could never support it. Okay, so the whole concept of the Dyson sphere is okay, but I thought of another one that might actually be, and it came from Freeman Dyson, the physicist. I thought of another one that might work, and that is a Dyson swarm. Now, it's on the NASA dockets to look at potentially having satellites that could beam energy to Earth to help our energy by taking energy from the sun, beaming some of it to Earth via, say, microwaves or whatever. And there'd be a receiving satellite station in orbit, which would then transmit it down to receiving stations on the ground, and we have energy. Yay! Okay? Well, we'd probably be very hungry for energy, so we would actually put up many more satellites. Okay? So you put up more of these satellites, next thing you know, you've got all these satellites, and from a distance far away, each of those little satellites is starting to block their starlight little by little. And over 100 years, maybe that image of the planet, or the star rather, is getting smaller because there's more satellites blocking it, as seen from here. So a Dyson swarm could be a realistic thought process. Jury is still out. We don't know. You didn't expect an answer, did you? I expect an answer, but we don't have one yet. And then part of the reason we don't have one has to do with our understanding of the universe. One of the problems we have is that that's the universe as we understand it. What does that mean? Okay. All right. Here we have 22% dark matter, 74% dark energy. I'll explain. And then we have these tiny little areas here. That little, 0.4%, okay, 3.6% intergalactic gas and stars. Those two things together, okay, make up what we understand. We know 4% of the universe. 96%? Anybody's guess. Okay? We call it dark because we don't know what it is. We don't call it dark because it's black. Okay, so you hear black hole, we know it's dark too, so it confuses you. What's dark energy? Okay, dark energy is a repulsive force, meaning it's nasty and gross. No, meaning everything that you put near it, it wants to push away. Why did we even come up with this? I think it's a cosmic fudge factor. I don't think it's real. Sorry. Okay, and I'll explain why. When Edwin Hubble, back in the 1920s, determined how quickly the universe was expanding, because we went from the universe isn't changing, the universe is collapsing, to the universe is expanding. Okay? And we determined it's actually expanding. When he determined that, he figured out something called the Hubble constant, which wasn't. The constant was, it's expanding at a certain rate, and that's a constant rate. Okay? So a speed of whatever amount. Okay, say 70 kilometers per second per megaparsec, that's how it's characterized. So a certain speed per a giant swath of distance. Okay, well, it turns out that with modern studies, guess what we found? It's moving faster. So the Hubble constant is no longer a Hubble constant. It's actually accelerating outward. Wow. Now, I'm going to give you a model for how the universe expands that you can remember. Show your kids, show your grandkids. Okay, show you yourself. Blow up a balloon about that big. Take a Sharpie, give it measles, put dots all over it, little black dots. And those dots are all going to be closely spaced. As you blow up the balloon, every dot will be moving away from every other dot. That's what we see. So what's that mean? It means now you got to extend that to 3 dimensions. Okay? Every single thing is moving away from every other thing, and that's what we're seeing. Okay? So what that says to us is that the universe is not only expanding, but it's expanding in a way where everything is moving away from everything else. Guess what that means? In the future, we're not going to have anything around us to see. Some future generations might have a black sky, maybe 1 or 2 stars, and that's it. And this leads to the whole thing of universe death, but we're not going to go there today. It's depressing, okay? But so this dark energy is interesting because when they found that it was actually accelerating outward, they had to employ the use of this repulsive force to say why it's accelerating outward. Well, think of it this way. When the Big Bang occurred, okay, it first starts, right? And when an explosion first starts, the very beginning of the explosion is an acceleration outward, right? It goes boom, and then it slows down and forms a steady expansion. Well, that accelerating expansion might be what we're in now. So what this tells us is that we got a whole bunch of things wrong about the universe, about its origins, how old it is, okay, what it's doing. And the cosmologists are the one pulling out their hair. That's why I still have my hair. I'm an astronomer. I'm not a cosmologist. Okay? And they be pulling their hair out because if the universe is different from what we always thought, that's a huge problem. Okay? And maybe it is. So dark energy is what's used to explain it right now. I think it's a stand-in for what's actually happening, but what's actually happening, I can't tell you. Now, one last thing about that, Big Bang. When the Big Bang occurred, they always say, well, it started from a primordial superatom, right? And then it went poof and blew up. Okay. Do you know how many of us believe that the primordial superatom was an infinitely small point? 0. We don't think it was an infinitely small point. That's ridiculous. Just like a black hole, they say, is a singularity, a point, right? It's not. Why does a black hole have an event horizon that can get bigger and bigger and bigger the more mass it gets? Because the black hole's actually got mass inside of it, and it grows physically in size, okay? That 55 million light-year one we saw at the beginning in the Virgo galaxy, do you know how big that one is? If you put it where if you put it in our solar system, it would take up 6 full diameters of solar systems. That's how big that is. And considering it took 30 years for Voyager to get just outside our solar system, well, I mean, let's be clear, okay, that's an awful long time for Voyager to try to cross the face of a black hole, isn't it? Right, if it was that black hole. So it's a major sized black hole. So they grow in size. The event horizon is determined by the mass it encompasses. Anyway, so we're learning about the universe expansion. It's accelerating outward. And what does this mean for alien creatures? It means that alien creatures are subject to the same thing. And if they're coming from M stars, which I suspect they are, and some F stars, which I suspect they could be, Nordics, reptilians, grays, all of those types of creatures now and beings are plausible to me. They never were. Grays were plausible. I mean, it was a gray thing that shoved that thing up my nose. So you saw it, so it had to be there, right? But so the point is that the dark energy side, I'm sure they figured this out because they'd have to figure out dark energy and dark matter in order to actually get here. Because we only got outside our solar system by using that 4%. We haven't even used the rest. Imagine if we knew that, if we knew what was really going on there. Now, dark matter. Dark matter is a halo of matter around galaxies that we can't explain. And it's making them spin almost like a record album, like a solid disk. And that solid disk is something that we didn't expect. Mercury takes 88 days to go around the sun. Pluto over 200 years. Okay? It's moving much slower. The farther out you get, the slower you need to move to go around the middle. Well, in the galaxy, the center is moving fast, but the outside is moving faster than it should. It should be much slower. And we're seeing the stars go through the spiral arms of a galaxy. The spiral arms go around too, but they're going at a different rate altogether. And the stars are going like this, spiral arms are going like this. They go in and out of the spiral arms. It's a whole other talk I give about spiral arms and galaxies and why they look like they do, but that's no, it doesn't have anything to do with aliens, you know. So dark matter is something we don't understand. That's why it's dark. We don't know. So everything we know, we've done with 4% of the universe, everything. So for us, the epilogue is that, you know, as we search for extraterrestrial life in the universe can take many forms based on the stars we see and the potential for life on stars like that, the M stars, or the F stars like Tabby star, or the A stars like Fomalhaut, okay, and others. Life, HR 8799, the most romantic of the bunch, right? Okay, as far as life on all these planets, different life forms are going to find that life, and different life forms are going to develop there, and different life forms are going to find us. This could explain the different UFOs people see. Different civilizations will develop different technology, but they're all going to go through a nuclear era because the atoms are the same everywhere. They're going to go through a fission era like we're doing now with our energy. They're going to go through a fusion era that we're getting to. And they're going to go through the interdimensional era where they're going to allow themselves and be allowed to travel around the universe. We're getting there, right? But I believe they've gotten here. So thank you. We're done. If you have any questions, I'm happy to take a stab at it and pretend I know the answers.
You've got 5 minutes to take questions.
5 minutes. Okay. So whoever has a question.
Hey, appreciate you, man. I forgot the name of that cigar asteroid that came, I think.
Oumuamua.
Yeah. Can you speak to any anomalies of that one?
Yeah, Oumuamua was interesting because when Oumuamua was found, it was only found after it was leaving. You know, we didn't have it, we didn't catch it before it got, when it was on its way. We caught it after it left. And so Oumuamua was initially thought to be a cigar shape, like you said, but it turns out that it was actually a pancake. Right? It looked thin in cross-section kind of thing when they did the analysis, but it was actually like this. And so it tumbled, which could have explained a little bit about why it accelerated oddly when it left. Maybe that faced in and more solar energy hit it to kick it out. Maybe. Don't know. That's why Oumuamua is a mystery. Maybe it's extraterrestrial. Jury's still out.
All right. You said the black holes were expanding. Do we have any of those in our area that could eventually, like, encompass Earth?
No. When a black hole acquires mass, it does get larger in size. The thing that increases is something called the Schwarzschild radius. It's the radius of the black hole. The more mass that goes in it, the bigger that gets. And all that means is that that's the bigger it gets, the event horizon where light can no longer escape, that diameter grows. So a big one like this, 55 million light year one away, would have a very large event horizon. And another theory, which is really cool, which I'll just say real fast, that's a great question. No, they'll never threaten us. Another theory is that we're in a universe that is in a black hole. We're in a black hole, looking out from inside. I know, kind of weird. Yeah, thank you. That's a great question. But yeah, we're okay. We don't have any near us.
In your example you gave earlier with the balloon where everything's expanding out from itself, does that mean then where is the center of the universe?
Oh, see, that's a question I've always dealt with.
She says it's not me, but I disagree. But
Oh, no, it's her.
Well, she's right. It's not you. You can hit him for that. No, the center of the universe is something that we actually can't figure out. We don't know where the center is. There's no way to know that. And it's because it's been 13.8 billion years and we're observing it from one position. We can't reverse engineer because we can't see the whole universe. Here's the problem. We only see out 13.4 or so billion light years. Beyond that, the universe was opaque early on, and that's what we see, the early universe. But it took 13.4 billion years for that light to get here. And that's what we're seeing now. In that time, that expansion kept going. Right? In that time it took for that light to get here from all that far away. So the universe is bigger than that by another 13.4 billion years, light years, okay, and age, so to speak. However, you also consider the acceleration. The universe is going bigger and bigger and bigger every second. And that has changed things so that now the current estimate is that the universe is 93 billion light years in diameter. It's not 13.8 billion. That's only as far out as we can see because we're limited by the speed of the light bringing us that information. Isn't that crazy? It makes your mind say, I'm going to drink more than water later. That's what it does. Yeah. But that's a great question. Thank you.
What about gas giants? I mean, they have a wide variety of pressures and lightning and various the chemistry. What about life inside a gas giant?
That's a very good question. Now, I did an analysis of Venus, the Venusian atmosphere, because somebody suggested that there was a possibility for Venus to have life on it, okay, in the atmosphere. I don't have a thought process against that. I just look at the pressures of evolution of something like that. Its range of mobility is going to be limited. I don't mean mobility like movement. I mean mobility in the evolutionary scheme of things is going to be severely limited if you're an atmospheric object. Where are you going to get your food? Where are you going to get your sustenance? How are you going to reproduce? And how are you going to do it safely? Is there predation? Is there not predation? I don't know. But that's a very interesting question. I don't buy the one about Venus having any life in the upper atmosphere. Yeah, Jupiter doesn't have an atmosphere that's very conducive to life as we understand it, okay, because Jupiter's winds are hundreds of miles an hour, over 1,000 miles an hour in some places. We don't know a lot that can handle that. Not us for sure. Thank you.
This is the last question.
Thank you so much for that.
You're welcome.
Wonderful talk. How do you measure nickel on a comet?
That's an excellent question. When we look at the comets that we see, we can see the spectral signatures in the spectrum of nickel, okay? And so when we see the nickel, we also look for the iron. And you expect to see iron lines in the spectrum and nickel in the spectrum. We don't see that. We saw nickel only. That was odd. And again, it was that nickel carbonyl, that nickel with the carbon monoxide molecules, and 4 of them, okay, at 100 Fahrenheit, will vaporize and let the nickel go free. So I believe, not everybody believes, I believe, that's why the nickel became visible early. And then the iron became visible later because it takes 200 degrees Fahrenheit to liberate iron from the 5 carbon monoxide molecules around it. If that's what the carbonyls, and the iron carbonyl, nickel carbonyl, these are things that are available to be made. We can have that happen in a comet. But in our solar system, it's not exactly like we see in this, which makes it still an anomaly. Yes, we have an anomaly still, right? But still, think about it. That's pretty interesting.
So it's done with the telescope.
Huh? Oh, yeah, it's done with a telescope with a spectrograph. And for our Sky Tour live stream, we're creating a system. We're going to have a spectrograph on one of our systems, and we're going to have a whole world of spectroscopy that we're going to do to look for planets around other stars, and so it's going to be kind of fun.
All right. Thank you, sir.
Okay, thank you guys.